Good day, I am Carl Del Castillo, together with Mimbra Louis, Francis Ferranda, Justin Okiana. We will report to you our term and project entitled Design and Analysis of Heat Exchangers using Number of Transport Units and Effectiveness Method. So heat exchanger is a heat transfer device that exchanges heat from different fluids through thin walls. This transfer of heat from processed fluids is a vital constituent of most chemical processes of various industries with a wide range of domestic utilization, including power generation, transportation, and refrigeration units. So the word exchanger connotes any type of equipment wherein heat is exchanged, but is most often used to denote heat transfer between any two process streams. However, actual design of heat exchangers accounts for various factors and is a complicated problem that deals with more than just heat transfer analysis. Also, heat exchanger equipment must take into consideration the size, weight, cost, space, installation procedures, and the subsequent carbon footprint.
Next, we will be going through common heat exchanger equipment, their design specifications, and the concepts and principles associated with heat exchanger design. There are different classifications of heat exchangers, but for this particular presentation, we will be dealing with the three most used heat exchangers in the industry. Heat exchangers come in a wide variety of types and sizes. Other than flow path configurations, industrial heat exchangers can be further classified according to their construction, transport mechanism, degree of compactness, and etc. Over the past decades, the broad range of heat exchangers have ultimately developed, and with it the preference of most industrial industries with respect to different factors. Respectively, these are shell and tube heat exchangers, the plate and frame heat exchanger, and the double pipe heat exchanger. First, we will be talking about the shell and tube heat exchangers. This is the most used type of heat exchanger. More than 90% of heat exchangers in the industry can be attributed to this type. The shell and tube heat exchanger, or the STHE, has been utilized in the industry as oil coolers, condensers, and feed water heaters. The basic design of STHEs were first introduced in the early 1900s to accommodate the need for larger surface area heat exchangers. Following the decades, the steady increase in use of STHEs demanded the need for higher accuracy on performance prediction and thus increase in research and development activities. This does not only include shell side flow, but also computations on the true mean temperature differences and strength calculations on construction elements, making STHEs the most fabricated type out of all of them. The shell and tube exchanger accomplishes its cooling task by circulating a hot liquid around tubes which contain a cooler liquid. The hot liquid circulates in an enclosed area called the shell. Tubes containing the cooler liquid are looped through the shell. Hot liquid in the shell warms the cooler liquid in the tubes, whereas the cooler liquid in the tubes cools the warm liquid in the shell. Next, we will be talking about the plate heat exchangers. Dr. Richard Seligman, the founder of ABV International, introduced the first commercially gasketed plate heat exchanger design in 1923. A plate heat exchanger, or PHE, consists of a series of parallel plates that are corrugated, both to increase turbulence and to give mechanical rigidity. Plate heat exchangers are particularly suitable for heat recovery duties in the chemical, petroleum, food, dairy, and brewing industries. The basic principle works by allowing the process fluids to flow alternately at the corners to which the heat transfer between the plates are around each other. The corrugation of these plates increases turbulence and thus increases heat transfer rates, for which we know in shell and tube heat exchanger designs, the more turbulent the flow is, the higher its heat rate or heat transfer coefficient is. Lastly, we'll be talking about double pipe heat exchangers, or DPHE. These are distant cousins of the STHE, belonging under the same family of tubular heat exchangers. It is considered as one of the simplest and least expensive type of pipe heat exchanger systems. There are two common DPHE setups shown in the figure. The one on top is the standard DPHE, and the one below is its hairpin variation, or the U-bend variation. DPHEs can be used as alternatives to the conventional shell and tube design for different reasons, such as high pressure operations, small scale duties, or any process that necessitates true counterflow approach. Here we can compare the three heat exchangers in terms of their surface area and pressure temperature operating conditions. Based on these values, we see that the shell and tube design, or the STHE, and the double pipe heat exchangers, both of which are tubular heat exchangers, withstand wider ranges of temperature and pressure operations. For STHE, that's around up to 8,700 psi and from -20 to 500 Celsius. However, comparing it to the plate heat exchanger, which is particularly useful only between the two conditions, but due to its modular design, we can see that its surface area is comparatively smaller than the two designs, saving space and essentially being more cost effective than the other two heat exchanger designs.
The rate of heat transfer from the hot fluid is assumed to be equal to the rate of heat transfer to the cold fluid, with an assumption of no phase change, and specific heat of fluid is evaluated at bulk temperature. This can be expressed in terms of mass flow rates, specific heats, inlet and outlet temperatures, which can be shown in the equation below. Second is the log mean temperature difference, which is used to determine the temperature driving force for the heat transfer of flow. The computation varies depending on the flow configuration. The general expression for the log mean temperature difference, or LMTD, is shown below. Here is the difference with the calculation of temperature difference 1 and 2 if the flow is either parallel or counterflow. The NTU, or the number of transport units, is a method used to determine the rate of heat transfer if there is not enough information to know the log mean temperature difference. This usually happens when the fluid inlet or outlet temperature is not available. The heat capacity ratio, denoted by C, is the ratio of the lower heat capacity to the greater heat capacity. The C sub H or C sub C could either be the C minimum or C maximum depending on the computation. For the computation of maximum heat that can be transferred, the fluid with lower heat capacity is used under the assumption that the change in temperature would reach the maximum. After obtaining the parameters, the NTU is then obtained with the equation below. The heat exchanger effectiveness is a function of the heat capacity ratio and NTU, in which varies depending on the flow configuration. Formulas are obtained from Sengel's heat and mass transfer, fundamentals and applications, and a paper titled The Design of Shell and Tube Heat Exchanger, a review of Karthik in 2019, namely for double pipe parallel flow, counterflow, shell and tube 1 shell pass, 2 to 4 tube passes, shell and tube 2 shell pass, 2 to 4 tube passes, and cross flow wherein the both fluids are unmixed. And here are the three equations that will be used in the calculation in the succeeding slides. The actual heat transfer rate of the heat exchanger can be determined by multiplying the computed effectiveness with the maximum heat transfer which was obtained earlier. And moving on to application and discussion. So for the design description, here is the story problem for this paper. So as young inspiring chemical engineering students, your team has been tasked by Dr. Mike to select the best heat exchanger among the selected heat exchangers below. The inlet flow rate of the hot oil is 1.9 kilogram per second with an initial temperature of 85 degrees Celsius and a specific heat of 3000 joule per kilogram Kelvin. It is then cooled by water in a nearby lake with a mass flow rate of 2.4 kilogram per second with a specific heat of 4,180 joule per kilogram Kelvin and an initial temperature of 10 degrees Celsius. Assuming an overall heat coefficient of 2,450 watt per cubic meter Kelvin, which of the heat exchanger is best suited for the fluid? Due to economical reason, the client can only accommodate an area of 3 cubic meter. In addition, it is also important to determine the temperature of the outlet fluids for proper disposal. The heat exchangers to be evaluated are double pipe parallel flow, double pipe counterflow, one shell 2 for tube passes, two shell 2 for tube passes, and plate cross-flow heat exchanger, unmixed fluids. Assumptions include the following. The energy loss from the surrounding environment is negligible since the heat exchanger is well insulated. Assume that the heat exchanger operates at 1 second and is at steady state. Assume that the oil passes through the tubes without mixing and without direct physical contact. Assume that the oil-specific heat capacity is 3000 joule per kilogram Kelvin and of the water has a constant specific heat capacity, which is 4180 joule per kilogram Kelvin, which is also constant throughout the heat exchanger. Assume that the heat exchanger is new, therefore, the fouling factor is negligible. Assume there is no heat generation that will occur in the heat exchanger. So the physical properties of fluids and heat exchanger data are summarized in Table 3.1 and Table 3.2 as shown in the slide.
Good day, I'm Bryn Ivan Veluis, and I'll be discussing about our detailed computation that was computed through Microsoft Excel. So, for our term project, our problem is, as young, inspiring chemical engineering student, your team has been tasked by Dr. Mike to select the best heat exchanger among the selected heat exchanger below. The inlet flow rate of the hot fluid is 1.9 kg per second with an initial temperature of 85 degrees Celsius and a specific heat of 3000 joules per kilogram Kelvin. It is then cooled by water in a nearby lake with a mass flow rate of 2.4 kg per second. A specific heat of 4100 joules per kilogram Kelvin and an initial temperature of 10 degrees Celsius. Assuming an overall heat coefficient of 2450 watts per meter squared Kelvin, which of the heat exchanger is best suited for the fluid? Additionally, due to economical reason, the client can only accommodate an area of 3 meters cubed. In addition, it is also important to determine the temperature of the outlet fluid for proper disposal. So here are the 5 heat exchangers that needed to be evaluated. Number 1 is the double pipe parallel flow. Number 2, it is the double pipe counter flow. Number 3, it's one shell, 4 tube passes. Number 4, it's 2D shell, 4 tube passes. And letter E, it is plate cross flow heat exchanger. So here is the legend. You will for the color peach you will input the data, and the color yellow you will get the answer. So here is the solution summary of the problem here, and we will discuss on how it is derived. So we first input the data of the problem, which is 1.9, 85, and 3000 joules kilogram per Kelvin, and also for the cold fluid. So for the heat exchanger type, you can choose the five heat exchanger, which is the for the necessary data below. So uh, the Excel is computed by mostly of if conditions. So from the tables here, you can see from if one table heat exchanger, two counter for three shell and tube, four tube, and five cross flow. Okay. So for our calculation phase, so we just inputted the flow rate, inlet temperature, specific heat coefficient, heat transfer coefficient, area. So the outlet temperature will be discussed later. Uh, so here are the formulas for the outlet temperature that will be computed later. So first step, we must solve the C min and C max. So we will be using effectiveness method, so which is a function of NTU and C, where C is the ratio of the C min and the C max. Okay, So the C of the hot is mass flow rate of hot times Cp of hot. The Cp of cold is Mc of hot times Cp of cold. So here are the values of C hot and C cold. So as you can see, since the value of C hot is less than since the value of C cooled is less than C hot, so therefore the C min is equal to C hot and the C max is equal to C cold. Okay, so we can solve the value of C by dividing 5,700 by 10,032. Okay, so now we get the value of C. We must get the value of NTU. Okay, so remember, E is equal to the function of NTU and C. So yeah, NTU is equal to the overall heat coefficient times the area all over the Cmin. Since we get the Cmin a while ago, we can input here the value. So UA, we just times U times A, and NTU we divided by the Cmin. So we can get the value of NTU, which is 1.29. Okay, so once we get the value of NTU and the value of C, we can get the value of epsilon. So for the first type of heat exchanger, we'll be using the double pipe heat exchanger for parallel flow. So for the formulas to get the value of epsilon or the effectiveness, so from Sengel Introduction to Thermodynamics and Heat Transfer Second Edition, table 16.4, we can get the derived formula, which is E is equal to 1 minus EXP times the quantity negative NTU times the quantity 1 plus C all over 1 plus C. Okay? So since we get the value of C and NTU, we can just input it into our Excel. So for the calculation here, epsilon, as you can see, you can just input NTU and C to get the value of epsilon. Okay? So once you get the value of epsilon, the next step is to find Qmax and the heat rate. So Qmax, the formula of Qmax is equal to Cmin times Th of in minus Th of out. Th of in. Sorry. Okay. So what is Cmin? Cmin is 5,700 times Th of in, which is 85 degrees Celsius, and Th of out is 10 degrees Celsius, which gives us a value of uh, the value of 427,500 watts. Okay. So once we get the value of Qmax, we can now solve the value of the actual value of Q, the actual heat rate. So the actual heat rate can be computed by multiplying the epsilon and the Qmax. Okay. So once we multiply that, we can find the value of the heat rate, which is 236,523. So for bonus, we can also solve for the logarithmic mean temperature difference. So the logarithmic mean temperature difference is equal to delta T minus delta T2 all over ln delta T1 delta T2. Note, for parallel flow, delta T1 is equal to TH in minus TH out. So hindi TC in. For delta 2, it is TC out minus TC in. So this is for counter flow. That's why nakalagay. But for keep note, if it is equal to 1, here table F3 is equal to 1, this equal to 1, it is double heat exchanger parallel flow. TH delta 1 is equal to TH in minus TH out, and delta 2 is equal to TC in TC out minus TC in. Okay, so that's why the value here is 75 degrees Celsius, and delta T2 is 9.9 degrees Celsius, and the logarithmic mean temperature temperature difference is 32.18 degrees Celsius. Okay? Once we get the value of that, we can now summarize in the solution summary. So, uh, okay, the outlet temperature. So the outlet temperature can be solved by mass flow rate of H times CPH times TC in minus TC out, and while the TC out can be computed by Q is equal to MC times CP cold uh, times quantity TC out minus quantity TC in. So using that values there, we can get the value of temperature out and the temperature in. Okay. So okay. So we get the value of the temperature, outlet temperature. We get the flow rate times specific heat, and we get the LMTD. But um we're asked for the Q. Okay. So the Q is our final answer is 236,522.58 watts. While here are the values of NTU, which is the number of transfer units, and heat capacity ratio, and our effectiveness. Okay? So, for ano naman, double pipe heat exchanger, it is also the same procedure. First, we get the C min and C max. Then we get the NTU. Then we get C, epsilon, then Q max, then outlet temperature, then the heat rate. Okay? So, uh, for double pipe counterflow, here is the formula. So, as you can see, straight substitution, here siya. May NTU ka, may C ka, yeah. Say, ano siya, direct substitution that we'll put in Excel. Okay? So for one shell tube, same values. However, this is the one of key thing to note. For two shell and for 8 tube passes, wala siya actually sa book from Sengel. That's why we found the formula from Kartik 2019. So first, E is equal to here. It is the family here. And NTU1 is equal to NTU over N. While N, it is the number of shell, the number of shell. So this is 2 shell, so this is number 2. So to get for the value of E1, it is the same of 1 shell siya, but you will need to use the NTU values. Okay? So, okay. So for example, here, we use 2 shell tube. Okay? So we get the value of hot and cold, specific heat, C, and NTU. Okay? So for solving epsilon for 2 shell for 8 tube passes, the first thing that I did is to separate it, parang hiwalay-hiwalay siya. And you can get the square root of 1 plus C squared here. NTU1, which is basically NTU divided by 2. NTU divided by 2. And E1, it is here. Basically, you will just use the value of NTU. It's the same of here as 1 shell 2 tube, but you will use the value of NTU divided by 2. Okay? Once you get that, you can solve the value of the actual E, which is this formula here. So, yeah, after you get that, N is equal to the number of shells. N is equal to the number of shells. Okay? So, yeah, after that, you can choose what watts. You can get the number of watts that are required and the temperature of the outlet and the temperature of the hot fluid. Okay? Yeah. So that's all for the detailed computation. In continuation with the Excel file, The following 5 exchanger data was then gathered and summarized in table 3.3. So its number of transfer units, heat exchanger effectiveness, and heat transfer rate were then evaluated in the next slide. So as you can see in table 3.4, the most effective heat exchanger among the 5 heat exchanger that were selected is the double pipe heat exchanger counterflow with an heat exchanger effectiveness of 0.6631. It is then followed by shell and tube, 2 shell, 4, 8, 2 passes. Number 3, plate cross flow heat exchanger, both fluid and mixed. Number 4, shell and tube, 1 shell, 2, 4 tube passes. And number 5, double pipe heat exchanger, parallel flow, respectively. In conclusion, this project aims to evaluate the most efficient heat exchangers from the 5 different heat exchanger, which are the double pipe parallel flow, double pipe counterflow, 1 shell, 2, 4 tube passes, 2 shell, 2, 4 tube passes, and the plate cross flow heat exchanger mixed from cooling hot oil using water. So the most effective heat exchangers that we concluded is the double pipe heat exchanger with a heat exchanger effectiveness of 0.6631. This is supported by the higher heat transfer rate, thereby reaching thermal equilibrium much faster. Additionally, this is evident with the two outside stream having the lowest change in temperature, with temperature of the hot liquid being 37.50 degrees Celsius and the temperature of the cold liquid being 36.98.
And going to the last portion of our presentation, we have here some of the frequently asked questions. First off, what effect does the surface structure of heat exchange tube have on the heat transfer effect? To answer that, it increases the heat transfer area and the turbulence effect. This special surface greatly increases the turbulence degree of the fluid outside the tube, both of which can improve the overall heat transfer effect of the heat exchanger. So the performance of these surface structures is better than that of the smooth surface. So question 2, what are the common methods to enhance heat transfer of the heat exchanger? And I'll make this brief. So one is to adopt the structure of increasing heat transfer surface. And secondly, the heat transfer coefficient can be greatly improved by increasing the flow rate of the fluid in the heat exchanger. So question 3, in the tubular heat exchanger, why are the diameters of 32, 25, 19, and 16 selected respectively? So the answer would be the size of pipe diameter will directly affect the performance of heat exchanger. So small diameter, large heat transfer coefficient, and large effective heat transfer area in the same volume. So for the fluid with the same flow rate, the smaller the pipe diameter, the greater the resistance when flowing, and the pressure loss will also increase. And in addition, the pipe is too thin, it is easy to be blocked by dirt, which makes cleaning difficult. So therefore, the diameter of heat exchanger is generally 16 millimeter to 32 millimeter. So these are our references and the credits. And that's the end of our presentation. Thank you for listening. Have a wonderful day.